Brad Williams, Frugal Finance, continuous compounding examples. Continuous compounding simplifies the calculation of interest when it's constantly being added to an amount of money. For example, if $100 and the interest rate is 10% annually, continuous compounding after 1 year, you'd have 110.52. All right, no surprise, pretty straightforward. That's simple. When dealing with interest rates that compound yearly, semi-annually, or in other frequencies, there's a formula to find the equivalent continuous compounding. Well, we know that. It's EXP, R to the N. It's like converting different currencies into one standard currency. For example, if a lender offers an 8% interest rate per year with continuous compounding, but interest is paid quarterly, you can use the formula to find the equivalent rate for quarterly compounding. Bond pricing also involves calculating the present value of all future cash flows, including coupon payments and the bond's principal repayment. This can get complex because each cash flow might have a different discount rate. For example, a 2-year bond with semi-annual coupons, you discount each payment at a different rate. I previewed this earlier. I didn't explain it, but I used different discount rates because they're semi-annual compounding. To find the theoretical price of a bond, you add up the present value of all of its future cash flows using the appropriate discount rates. This often requires an iterative process to find the exact yield that matches the bond's market price. The par yield of a bond is the coupon rate that makes its price equal to its face value. It's usually calculated assuming semi-annual coupons. You can find the par yield by setting up an equation that balances the present value of the coupons and the principal repayment with the bond's market price. We've used this EXP to derive the continuous compounding for 10% with semi-annual payment. No magic there. When working with interest rates that are measured with annual, semi-annual, or some other compounding frequency, use the following. Use the tools. We are comparing equivalence. Again, we're using that word equivalence. So consider an interest rate that is quoted as 10% per annum with semi-annual compounding. M is equal to 2, and R of V is equal to 0.1. The equivalent rate with continuous compounding is 9.758. We're using this tool here. And then you just convert this back over to 10% we're just using this formula. And then we're using this formula for this. Okay. We've gone over this time and time again. Don't sweat. Use what you have available. Suppose that a lender quotes the interest rate on loans at 8% per annum with continuous compounding. That interest is actually paid quarterly. Use this formula. Remember I said you're just going to do some multiplication here? We're going to use this formula. We've used it in the past with M is equal to 4 and RSC equals 0.08. Here we just have 8.08. We use 4, M, 4, times EXP, 8 divided by 4 minus 1 gives 8.08. 1,000 times this formula, 8080. It's paid quarterly. Divide that by 4. Bond pricing. Most bonds pay coupons to the holder periodically. The bond's principal, which is also known as its par or face value, is paid at the end of its life. The theoretical price of a bond can be calculated as the present value of all the cash flows that will be received by the owner of the bond. Sometimes bond traders use the same discount rate for all the cash flows underlying a bond, but a more accurate approach is to use discount zero rates for each cash flow. What are those rates? That's what we're getting to. To illustrate this, consider the situation where Treasury zero rates measured with continuous compounding are in table 4.2. That's right here. Remember, I used those numbers before. The reason being is once we get into forwards, we'll calculate these using zero coupons. And what? Yep, baby steps. Suppose that a 2-year Treasury bond with the principal of $100 provides coupons at the rate of 7% semi-annually. Calculate the present value of the first coupon, $3, we discount it at 5% for 6 months. Right here. There's half a year, 5%. To calculate the present value of the second coupon of $3, we discount it at 5.8%. We discount the next at 6.4% and the last at 6.8%. There's no easy, fast, simple way to do this. It's just crunching the numbers. And there's no magic here. All we're doing is filling in the spaces. Semi-annual coupon times EXP times the rate times the period plus 3 times EXP, the rate times the period, and so on and so forth. And we're going to come up with a discounted price of 98.39. This problem can be solved using an iterative trial and error procedure to give us 6.27 to come up with the rate. We've done this before. What we're going to do is we're going to take this formula, we're going to equate it to this trial and error number, 6.7 D62, and then you just plug and chug. You change this number. It has to equal 98.39. What we do is we take the same number, 3D1624, and do trial and error to come up with $100, 6.27, and then 97. So again, I do a lot of scribbling. The question is, what rate takes us back to par value? And then what is this 9709? D65, we have to go back up. You can't hard code all of this. There has to be something that's changing. So this must be D65 right here. This problem can be resolved. 6.76 equates to this discounted rate. Par is 6.27. And then this is the discounted rate at 100. Now keep in mind when we're doing this, we have this par yield continuous compounding. The par value of a certain bond maturity is the coupon rate that causes the bond price to equal its par value, principal value. Usually the bond is to provide semi-annual coupons. What we have to look at here, suppose that the coupon on a 2-year treasury bond, here's our term structure here. In our example is C per annum, or 0.5% per 6 months, using the zero table. In table 4.2, the value of the bond is equal to its par value of 100 when it looks like this. Here is our structure. We have 5, 5, 8. We have to use, remember this wicked looking formula? Well, all we're going to do is plug and chug. Now it's hard coded, but it's hard coded for a reason. It's illustrative. So all we're doing is we're going to take C72, trial and error. We're going to use this puppy right here. And then all we're doing is using what we've used before. What do we have? We have a half a year and we have 5% right here. Then we're going to take C72. It's compounded, semi-annual. We're going to take ESP, 5.8. And that's for year 1. I said 5%. I had these backwards. 5% for the first 6 months. Then we're going to take the 5.8 1 year. Then 5.8 times 1.5. Then we're going to take the 6.8 C62 divided by 2, C64, 172. Then we're going to take the 100, and all we're doing is discounting all of this. It has to equal our par, which is our maturity of 100. And this is just a matter of just practice and just trial and error. That's it. Now, more generally, if D is the present value of a buck received at the maturity of the bond, A is a value of an annuity that pays $1 on each coupon payment date, and M is the number of coupon payments. What are we deriving at? What are we looking at doing here? We have an annuity. We have 100, which is our value. We have 2 periods. We have this 6.87, and we derive this by 100. Minus 100 times C87. So we're going backwards here. We're using a 0. So we have C87, which is this 87284. And then this 87284 is this 6.8. That means we're looking at the discounted price today, 687, in order to derive at all of these other numbers. I think we're going to have, nope, we're just looking at this information, and our discount factor is D81. Here's our D81, which is the 687, which is our discount factor. This would be our compounding factor, 87284. So where does this come into play? We have a zero price today. A equals 370. Our confirmation would be to plug this D81, and that's this 687. And 687 is 100 minus 100 times C87. You see we're going kind of circular here. And this is the same number. We looked at the discount price today. That is the 682 times 2. Everything revolves around this zero coupon and discounting it back at the current price, which is EXP 6822. And then A is equal to this, which we've used time and time again. There you go. Where did we start here? We started at continuous compounding. Continuous compounding is a challenge on its own. Then we start messing around with zeros. Then we start looking at par value. Then we reverse it. And then we want forward pricing. Then from forward pricing, we want annual compounding. And then from annual compounding, we want continuous compounding. It's all integrated, but it's not simple to understand. This is an introduction to more complexity down the road. So my suggestion is to go through, reread this, and work through repeatedly this continuous compounding. Ask yourself, why is this what it is? Then go back and look at our equivalents. Then throw in this bond pricing. Then throw in the par continuous compounding and work through it. A lot of this over here is me doodling. Why do I doodle it? Because when I'm working through this, I have what ifs. And when I have what ifs, I can think, but I like to draw it out. And this is sort of a map, and they're hints. I don't want to give away everything, but I want you just to work through this piece by piece and don't walk away. Don't think you're going to be able to solve this the first time around. This is something that maybe you'll look at early in the morning, and then maybe later in the evening, you'll just glance at it. And then tomorrow, after some rest, you can come back, you'll go, okay, I see it. The formula confirms that the par value is 6.87 per annum. With continuous compounding, it would be 6.76 per annum, see D62. So here we have our semi-annual, and this looks like continuous. This is continuous. This is our semi-annual example. Brad Williams, Frugal Finance. Thanks for watching.